Hello my shimmering stars, today I Shaurya Grover welcome you all to this amazing platform of PW English. I welcome you all students to your own Nexus Batch, and today we are going to start with lecture number 5 based upon your chapter Classification of Elements and Periodic Properties. So students, we have already covered classification of elements, we have already covered atomic radii. The atomic radii variations we were doing, only one of the topic was left, but yes, we have started the periodic properties. So you very well know what are periodic properties, right? We have discussed that we have to cover atomic radii, we have to cover ionization energy, electron gain enthalpy, electronegativity, all of these periodic properties, yes. So atomic radii up to 90% we have already completed in the previous session, yes. So today we are going to complete first of all the atomic radii. Then we are going to further study about the periodic properties. So I guess you all are ready for this wonderful session. So yes, let us start this with the beautiful smile students. As I've already told you, we are going to start our lecture number 5 today. Yes. So what are we going to cover? How are we going to proceed? What are the topics? What are the targets for the topic? So the very first is variation of atomic radius that we were doing. We'll complete that. Next one will be ionization enthalpy, or in some books it is written ionization energy also. The next one is electronegativity, and the last one is going to be the trends along the period in the group in ionization enthalpy and electronegativity as well. Many of your students may think that ma'am, after ionization enthalpy, electron gain enthalpy, electron affinity is there and you are directly going on to electronegativity. Let me tell you, electron gain enthalpy and electron affinity is a concept which is very interesting one, and I know that there are so many exceptions in the variation section also. So that will require a different session. That is going to be the next session, of course. So that's why I've taken electronegativity first, and then we will be covering that. It's one of the same thing. No problem. We have to cover the syllabus, yeah. So, let us start with the very first topic, but here are your friends. So, they all are welcoming you to your session first of all, and here they are saying that have you revised your yesterday's class? Why they are saying that? Because in yesterday's class we have covered about atomic radius. Yes students, we had already covered atomic radius, and now it's time to discuss about the topic atomic radii variations. We have to cover the variations segment. So first of all, I will give you a quick recap of what we have done in the previous session so that we can, relate to the topic that we are going to start today. Yeah? Okay, ma'am. So first of all, students, variations of atomic radii, if I am talking about atomic radius or radii, it's one of the same thing. We will be talking about variations in the period, variations in the group students. Yeah? But first of all, I shall be starting with period. In the period ones, I have already told you the variation of, the second period, if you remember. If not, let us take a quick recap. Before that as well, let us discuss the factors that affecting the atomic radii. That one of the factors is nuclear charge. More the nuclear charge, size will decrease because it will attract the outermost shell valence electron. Yeah, what is atomic radii? The distance from the nucleus to the outermost shell electron is atomic radius, right? So if I am saying that nuclear charge is increasing, nuclear charge is the attractive forces between both of them, which nucleus is exhibiting on the electron. If I am saying that nuclear charge is increasing, that means electrons is coming towards inward. It is coming towards the nucleus. When it is coming towards the nucleus, that means size is decreasing. So nuclear charge was inversely proportional to size. Moreover, one of the factors is shells. If you are increasing number of shells, that means 1, 2 and 3 and 4 and so on, the distance from the center to the outermost shell is increasing, that means size will increase. So that means nuclear charge is inversely proportional to size and shells is directly proportional to size. Yes? So this was about the thing that we have already covered. And one more thing, we studied that van der Waals radius was the one which has the largest radius in comparison to the metallic and in comparison to the covalent one. That's why in the second period when I was discussing the trend, we saw that neon had the highest radius and fluorine has the least radius. Let us write it over here. So I guess now your revision is also done when I have discussed this. Let's talk about second period again, students. Let's talk about second period again. So if I am talking about second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. These were my elements in second period. Yes, of course, ma'am. So when I'm moving from left towards right, when I'm moving from left direction towards right direction, what I am observing over here? I am observing that nuclear charge increases. Why nuclear charge increases? This is a symbol of increase. Why it is increasing? Ma'am, because number of protons are increasing. That's why nuclear charge is increasing. Now, what about shell, ma'am? Shell is same. N value is same, which is second. So that means attractive forces are increasing. If nuclear charge is increasing, attractive forces are increasing. Attractive forces are increasing. That means it is pulling the electron towards the innermost portion. Yes, to the centermost portion. So size will decrease. Ma'am, hence size is going to decrease. If size is going to decrease, what will be my order? Ma'am, my order will be like this, that lithium should have the highest atomic radii. But this order was wrong. But this order is wrong. Why this order is wrong, ma'am? Because neon exhibits which kind of radius? Van der Waals radii. Neon exhibits which kind of radii? Van der Waals radii or van der Waals radius, due to which it has the largest size. Hence, our new order comes out to be what? Our new order comes out to be neon. It will have the highest one. Then it will be lithium. Then it will be beryllium. Then boron. Then carbon. Then nitrogen. Then oxygen. And at last, fluorine. Yes? So, this is going to be our trend for this particular case. Yes, everyone? This is for second period. This is the trend for which period, ma'am? This is the trend for second period. Clear? This is the trend for second period. Everybody write it down. Everybody write it down. I am going to start with the third period now. If everybody has written, now comes the exception section. Here also we have seen that there is an exception over here. If you don't remember, students, I am writing it all over here again, that van der Waals radii or van der Waals radius is the largest, and after that we have metallic one, and at last we have what? At last we have covalent radius. So this is what we have discussed in our previous session also. Yes, everyone, clear? Shall I move on to the next one where I have third period? Now, students, here comes the next part where I shall be discussing about my third period in the periodic table. So, we are talking about the third period in the periodic table. Students, what will happen if you are moving from left towards right direction? What will happen if you are moving from left towards right direction? This is your left, this is your right hand side, right? So now students, you basically know it's very simple, ma'am. This is third period. That means N value. That means shell value over here is what? Third, 3, right? If they have same shell. Now what is same shell? If someone don't know, this is your nucleus, this is your first shell, your second shell, your third shell. It is something like this, right? The structure will remain same, just the number of protons are going to change. Over here, the number of protons will change, which the nucleus holds, right? So what do we observe? That, ma'am, when we move from left to right, our nuclear charge increases. Why nuclear charge increases, ma'am? Because number of protons, ma'am, they start to increase. That's why. Now again repeating, if nuclear charge is increasing, ma'am, size should decrease. Size should decrease. That means this should be our order. This should be our order, but let me tell you students, this is incorrect. This is incorrect. Why so, ma'am? The same reason as we did in second period, no, students. It is quite different from the previous one. How it is quite different from the previous one, if I'll ask you? Everybody, I'm giving you a minute in order to write the electronic configuration of all the elements which are present over here. Electronic configuration of all the elements that are present over here. It is going to be 4s2 3d1. It is going to be 4s2 3d2. It is going to be 4s2 3d3. It is going to be 4s1 3d5. It is going to be 4s2 3d5. It is going to be 4s2 3d6. It comes out to be 4s2 3d7. It comes out to be 4s2 3d8. It comes out to be 4s2 3d10. And it comes out to be 4s1 3d10, and it comes out to be 4s2 3d10. This is the electronic configuration, students. Everybody first of all write it down. Everybody first of all write it down, then I will be letting you know, I will let you know what is the reason. Done. I will let you know what is the reason. I am writing all of these elements over here again. Yeah, I am writing these elements over here again. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Everybody first of all write this down. Also I am writing this point above over here so that you can mention. Here I have written with green color that size will decrease. Yeah. So basically I am writing it all over here again. Everybody write it down first of all. Then I'll let you know what is the exception. Here you can write, wait, I'll write it over here. Here you can write this is your exception. Here I am going to write the exception. Everybody return. Shall I write it down now? See, till manganese, student, till manganese what will happen? Till manganese nuclear charge increases, hence size decreases. Till here, students, what happens? Till here nuclear charge increases, size decreases. Okay, nuclear charge increases, size decreases. That means over here, till here, there is 3d1, 3d2, 3d3, 3d5. Over here, there is no electron-electron repulsion. Why, ma'am? Why, ma'am? Just see over here. In scandium, if I'll talk about, let us talk about the 3d series. Here, it has only one electron. In titanium, if I'll talk about, how many electrons in D? It is 2 electrons. In vanadium, if I'll talk about, how many electrons over there? 1, 2 and 3, ma'am. In chromium, if I'll talk about, how many electrons over here, ma'am? 1, 2, 3, 4 and 5, ma'am. Similarly, in manganese, there are 5 electrons. So, what are you observing over here? That there is no electron-electron repulsion because each orbital is containing one electron. That means over here, from scandium till manganese, this factor is being affected. This factor takes into account where nuclear charge is, you know, the one which is major one. So, size will decrease. But what will happen? What is going to happen next? Here if you are going to observe, in all of these cases, their size will become equal. What will happen to their size, ma'am? Their size will become equal. Their size will become equal of iron, cobalt and nickel. Why? What is the reason? What is the reason their size will become equal? Over here, if you'll observe, from iron, cobalt and nickel, here you are going to see that nuclear charge factor and electron repulsion both are present in equal amount. So the size will remain same. Now how? Let me show you. For example, if you are going to write for manganese, it is the same 3d5, right? But after in iron, let us see in the case of iron, it is 3d6. That means 1, 2, 3, 4, 5 and 6. See here, electron repulsion is occurring. Let us talk about in the case of cobalt. How many electrons in cobalt? 7. 1, 2, 3, 4, 5, 6 and 7. Electron repulsion takes place. Similarly, nickel if I have to draw. So 1, 2, 3, 4, 5, 6, 7 and 8. Again electron repulsion. So over here nuclear charge and electron repulsion, both the factor dominates. Hence it becomes what? Same. Now comes the end portion. What will happen as you are moving over here? As you are moving ahead, now electron repulsion factor will dominate. Electron repulsion factor will dominate. Now when it will dominate, see when if outermost electron is coming inside, inner electrons are repelling it and there is a huge repulsion, size will increase. Yes, so size basically over here increases. Got my point, everybody? So this is going to be our order. Everybody write it down so that I can move on to the next exception part. Done with this one, so that I can move on to the next exception part. Everybody please write it down. Exception 1, the correct portion 1 is written over here. This is the correct one. Clear, students? Shall I move on to the next one? This was variation again in which? Third period. Clear? Now we are going to start. You are going to pause the video and you can write it over there as well. We are going to start along the groups. Now in D block elements, S block elements I have already told you. Let us revise that first and then I will revise the D block ones, okay? So S block elements I have already told you in the previous class. In S block elements we have written hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. In this case, we have clearly seen that when we move from top to bottom, this is your top, this is your bottom, along a group. So when you move from top to bottom, what happens, ma'am? Number of shells basically, they increase. If number of shells are increasing, students, what will happen? If number of shells are increases, size basically will increase. So for S block elements, this was valid. Yeah, I've already written, no? But now if I'm talking about which case, I am talking about the case of D block elements. Here, what happens, students? You very well know that after lanthanum, there is lanthanoid series. After this, we have lanthanoid series from 58th element. So here we have lanthanoid series. Right? From top to bottom, basically size is going to increase because shells are increasing. But over here, in this 3D, 4D and 5D series, this is, it's fine. It's almost okay. But if you'll see over here, when lanthanoid series have started, okay, your trend should be that atomic radii should increase down the group. But in actual, what will happen? In actual, there will be an exception over here and over here. Why? Due to lanthanoid contraction. Now, due to lanthanoid contraction, what does lanthanoid contains? Lanthanoid will contain what? Very simple, ma'am. Lanthanoid contain D block elements, and we know that we have S block, P block, D and F block. We know that according to the screening effect or the shielding power, D1 will have the poor shielding. And in the previous session also I told you, if someone has poor shielding, that means its size is going to decrease. So hafnium and tantalum, basically their size will decrease and it will automatically become almost equal to their sizes. It will become almost equal to the size of the above element, of the 4D's element. Everybody write down this exceptions. Why it is occurring? Even you can write it due to lanthanoid contraction, due to presence of D subshell and D subshell basically has poor shielding, and if they have poor shielding over here, now D subshell enters. If they have poor shielding, no, if they have poor shielding, it won't protect and the electron will come inside, and when electron will come inside, size will decrease. So they will have almost a size equal to them. Now this occurs in which case? In the case of 3D, 4D and 5D series in the D block elements. Everybody done? Everybody done? Shall I move on to the next part if it is done, students? Shall we move on to the next part? Yes, done with this one. Now we are going to start with the P block elements, but first of all, everybody write it down. We will be writing for P block elements now. See, for P block elements, for example, we have group number. I am writing for group number 13th, okay? That is your boron family. Now see, boron family is boron, aluminium, gallium, indium and thallium. This is our boron family. Now see, as per the order, we should move from top to bottom. So number of shells increases. That means period increases. Number of shells in other terms is period. If period increases, size will also increase because the distance from the center to the outermost electron increases. So order, ma'am, should be like this. It should be like this. But students, it is incorrect. So ma'am, why it is incorrect? Why it is occurring over here, right? See students, what will happen over here? First of all, if you will see in the case of gallium, here due to presence of d orbital, d block contraction, due to presence of d orbital, what will happen? We know that d orbitals have poor shielding. So they won't shield. Now what I am saying again and again, shielding is, you know, protecting the nucleus so that outermost electron cannot come inside. This is what is shielding. And if someone is creating a shield, who are creating the shield? Inner electrons are creating a shield. If they're not letting the outermost electron to come inside, that means they're creating a shield, that means they're pushing it away. So if it is poor shielding, it is not able to, you know, they are not able to protect it. See, D block elements basically here, they are not able to protect it. They have a poor shielding effect. If something has a poor shielding effect, what will happen? It will come inside. Size will decrease. If it is poor shielding, they cannot protect, it will come inside. If they have good shielding, it will repel it, it will move outside. Repeating again, if it is a poor shielding, that means it cannot protect it, electron can come inside. But it is a good shielding, it will repel it, electron will go away. Yeah. So poor shielding, size decreases, good shielding, size increases, right? So size will basically decrease. That means if I am writing again all the elements over here, it is boron, aluminium, gallium, indium and thallium. What do we see over here? So it increases, no, basically over here it is approximately equal, or basically aluminium basically will have a little bit higher because it will reduce approximately equal, aluminium is a little bit higher, right? Next is the same case. Now in indium and thallium also the same thing occurs, but everybody first of all write this down. Done? Now students, over here also again contraction will occur in the same case. In thallium we have F block. F block have more poor shielding than comparison to the D block. More poor shielding. Now this is this basically the contraction of D block elements and all of these in thallium basically, if I'll talk over here. Here this is due to lanthanoid contraction. Everybody write this reason down. This is due to lanthanoid contraction. As you can see in this case, in last one case, in this case, lanthanoid contraction will occur. Lanthanoid contraction, presence of F orbital over here, F orbital will come over here. Okay, in this case D orbitals, lanthanoid contraction already explained you in 3D, 4D and 5D. Yeah, same can occur in this case, right students? Same will occur in this case. Because see, if you'll see that this comes under which period, this comes under which period, second period, third period, fourth period, no, fifth period. So in all of these cases, in this basically d orbital is responsible, in this basically f orbital is responsible. Yes, everybody. So over here, due to f orbital, it will have poor shielding, so size will decrease, hence it will have almost equal size. So this is going to be the order for the p block elements, students. Clear, everyone? Everybody please kindly write it down so that we can move on to the next part of ours. Everybody please write it down. Done. So this ends our, students, the atomic radii variations. Now we have completed the atomic radii variations very well. Now we shall be starting with the next topic, that is ionization enthalpy. What do you refer to as ionization enthalpy? Let us take an example, and with the help of that example I will explain you its definition. So for example, my dear students, I have this nucleus. Okay, this is my first shell, let us consider my second shell, let us consider this my third shell. And in this third shell, I have this electron. So what basically is ionization enthalpy? It is basically the amount of energy required in order to remove this electron from the outermost valence shell. What I am saying is energy required in order to remove this electron. From the outermost valence shell. Now we are going to remove this electron from whom? Isolated gaseous atom. From whom? From isolated gaseous atom. What do you refer to as this term isolated? Isolated means single, gaseous means, see, in the case of solid, atoms are so closely attached to each other, you cannot remove in that way. This can only occur in the case of gaseous one, right? So basically, and in this case only you can form cation. So basically what will happen, how cation will be formed? See, when an electron goes, a cation is formed. Cation is something which has a positive charge. Let me explain you again. Energy required to remove electron from the outermost shell, or energy required to remove valence electron from the outermost shell from an isolated gaseous atom is ionization enthalpy, or is ionization energy. Clear? That means how much energy I will give to do this electron so that it can be removed is ionization enthalpy. So basically it is defined as amount of energy required to remove the most loosely bounded electron from an isolated gaseous atom to form a cation. Now how, ma'am, cation is formed? Can you please explain this as well? See, let us consider I am a neutral molecule. Now neutral molecule is something which has an equal positive and equal negative charge. Yeah, if I am removing a negative charge, I am removing, electron is negative charge, no? I am removing a negatively charged particle. So I will be left with what? I will be a positively charged one. Now if I am a positively charged one, I am a cation. So this is what is saying that a cation is formed when one electron is removed from the outermost valence shell. Clear, everyone? Quite easy. Now it is measured in kilojoule per mole, kilocalorie per mole. Okay, now, and also in electron volt, right? Now students, basically there is successive ionization energy. What is successive ionization energy? You are removing one electron after the another. For example, if you have any element M and you are basically providing it some energy, ionization energy 1, in order to remove one electron, it will form cation 1. Why? Because one electron is going, so it will acquire positive 1 charge. If 2 electrons are going, it will acquire plus 2 charge. So what happens? Initially you have a element and you are removing one electron. So what will form? You will form its cation and one electron is liberated out. So the energy that you gave over here is ionization energy 1, which you gave at the very first step in order to remove the first electron. Now see the next part. Here you have formed M positive. Now again, when you have removed one electron, now you are removing one more electron. Now energy required to remove one more electron, that means the second electron, is ionization energy 2 that you are giving, and it will remove one more electron. Now what it will form? It will form M plus 2, because it was initially M plus 1. You are removing one more electron, it will become M plus 2. Now from M plus 2, if you are removing one more electron, it will become M plus 3, and you will give what energy? Ionization energy third. Now see, which of the following is the highest one? Ionization energy third is the highest one. Why, students? Always remember this order, that ionization energy third will be highest, then it will be the second one, and at last it will be the first one. Why is it so, ma'am? Why is it so, ma'am? See, this is successive ionization energy order. See, when you removed one electron, you required some amount of energy. For example, let us consider we have 4 protons and there was one electron that we removed. When one electron was removed, Okay, total 10 electrons were there. 1 electron is removed. 4 protons were holding force on 10 electrons. When 1 electron removed, 9 electrons are left. Now 4 protons will give more force of attraction to the 9 electrons left over, because the number is removed. If numbers are less, so it can pay more attention, no? For example, if you are giving an exam and there are 50 students in the class, if 10 students have gone away, not went away, have gone away. So my focus will be on 41 and I will be so clear that yes, 10 students are gone, so I have to focus more on 40. I can pay more attention to them. That means if you are removing one electron, its force will increase on the other electron so that they cannot go. That means more the force, more will be the energy in order to remove the electron. More the force, more will be the energy in order to remove it. That means ionization energy. Third, you have to provide a lot of energy because the force of attraction over here becomes so much strong. Clear, students? See, whenever I am explaining you something, it's your, it's your responsibility to write in your own language in the bracket in your notes. Then only it will be helpful for you, students. Clear? Okay. Let us now, students, move on to the factors that affect the ionization energy. So the very first factor that I am talking over here is the size of atom. Is what, ma'am? Is the size of atom. How size of atom affects the ionization energy? Let us consider this. See, for example, if this is my first, it has 2 shells, okay? And this is my one nucleus which has 5 shells, 2, 3, let us consider 4 shells. This has 2 shells, this has 4 shells, okay? And here is electron in the outermost shell, here is electron in the outermost shell. What is ionization energy? Ionization energy or ionization enthalpy is something when we are giving some energy in order to remove the electron from the outermost shell. So if I have to give energy to this electron to remove from the outermost shell will be ionization energy of this. And if I have to give some energy in order to remove will be the ionization energy of this. Let us consider this is A atom, this is B atom. So ionization energy for A is greater or ionization energy for B is greater. Energy enthalpy is the same thing, right? So see, students, what happened? Here the distance between the center and the electron is very less. So it is having a greater force of attraction. Here it has a greater nuclear charge, or I can say in bracket the force of attraction. What is nuclear charge, students? Nuclear charge is basically the attractive forces that nucleus exhibits on the outermost shell electron. So over here it is more because distance is less. Here distance is small, so it will exhibit greater nuclear charge. If you'll see over here, the distance is larger, the distance is wider. If distance is wider, attractive forces will be there between positive and negative, but not more as compared to the first A atom. It will be there in B, but not as much as in A, right? So less nuclear charge because distance is more. Because distance is more. Hence, here ionization enthalpy will be provided more. So I can say ionization enthalpy in the case of A will be greater than the B. Why? Because distance is less. That means lesser the distance, more the ionization energy. Why? Because force of attraction is larger. So we can say that ionization enthalpy is inversely proportional to size or atomic radii. Lesser the size, more the energy, because force of attraction becomes larger. So I can say lesser the size or smaller the size, not lesser. Smaller the size, more the force of attraction, more the force of attraction, more will be the ionization energy, because you have to provide energy to remove the electron. So it will be more in number. Let us read it. Ionization energy decreases with increase in atomic size. That means ionization energy is inversely proportional to size. Clear, everyone? That's great, students. Everybody please write it down so that I can move on to the next part of ours. Next factor of ours. Now, students, comes the next factor, that is your nuclear charge. That is your nuclear charge. What is nuclear charge? In easy terms, ma'am, nuclear charge is the charge, in bracket write down force, exhibited by the nucleus on outermost shell electron. Force exhibited by the nucleus on outermost valence shell electron is basically the nuclear charge. Now, ionization energy increases with increase in nuclear charge. What I am saying, ionization energy, it will increase with increase in nuclear charge. Why? Because number of protons are increasing. See, you basically know this trend, no? You basically know na that nuclear charge increases, so size decreases. Nuclear charge is increasing, that means it is pulling the electron towards itself. Nuclear charge increases, that means it is pulling electron towards itself, towards nucleus, so size basically will decrease. If nuclear charge will increase, size will decrease, right? Now only we have seen size is inversely proportional to ionization energy. So ionization energy will increase. That means in short what we can say? In short we can say that nuclear charge is directly proportional to ionization enthalpy. Nuclear charge is directly proportional to ionization enthalpy or ionization energy. Clear everyone? Everybody write down this factor so that I can move on to the next factor. Now comes the next factor, that is shielding or screening effect. What is shielding or screening effect, students? Again the same thing. A shield created in order to protect the inner electrons from the outermost electrons. Let us write this. What is shielding effect or screening effect? What is shielding effect or screening effect? The shield created by innermost electrons to protect the nucleus from outermost shell electrons. And we know that the screening effect of S is higher, then P, then D, and then F. So D and F have poor shielding. Poor shielding, size decreases, ionization energy will increase. Got my point? So see, the electrons in the innermost shells which will act as a screen or shield between the neutrons and the electrons of the outermost. This is shielding effect, which I have already written. The larger the number of electrons in the inner shell, greater is the screening effect. It will, shield properly. And smaller is the force of attraction if it is shielding properly. Good shielding. If it is good shielding, that means it will repel now the outermost shell electron, size will increase. Size increases, ionization enthalpy will decrease. Clear? Now see, if it is poor shielding, that means it is not able to protect. Electron will come inside. Size will decrease. Size and ionization enthalpy are inversely proportional, so ionization enthalpy will increase. Clear, students? Quite easy. Everybody write it down so that we can move on to the next part. Done, everybody? That's great. Now comes the next part, that is penetration effect of the electron. This I have already told you, the penetrating power S, then P, then D, then F. Already told you the same thing. So poor the shielding, they have poor shielding. Size decreases, ionization enthalpy will increase. In this case, ionization enthalpy will decrease. Why? Because size increases. That's why. Next is electronic configuration. The most important factor, students. Most important factor till now. See, electronic configuration. So always remember, fully filled electronic configuration will require more ionization enthalpy. Then it will be half filled. Then it will be half filled electronic configuration. Half filled electronic configuration. And at last it will be partially filled electronic configuration. What I am saying is, this is the order for ionization enthalpy. You will require more energy in fully filled electronic configuration than in half filled and at last partially filled. Why? Because in fully filled it is stable, and you have to remove one electron from the stable configuration. So that is the highest value. Highest value. That means in electronic configuration, if it is fully filled electronic configuration, you will require a larger amount of ionization enthalpy in order to remove the electron from the stable ones, then from the half filled and then from the partially filled ones. Clear, students? Clear, everybody? That means, shall we move on to the next part if it is done? Everybody, I hope so you have written this. So you can read it. If an atom is exactly half filled or completely filled, then such an arrangement has extra stability and you require more energy in order to remove the electron. Now comes the variations of ionization energy. So let us start with period number 1. Let us start with period number 1. In period number 1, we have hydrogen and helium. See, when we move from left to right, what will happen? Very simple, ma'am. Nuclear charge increases, size will decrease, hence ionization enthalpy will increase, because size and ionization enthalpy are inversely proportional. So basically helium will have more. There is one more reason for this. What is the reason? Helium basically has 1s2 electrons. That means completely electrons, and hydrogen has only one electron, 1s1. It has 1s2 configuration, it has 1s1 configuration. This is partially filled or half filled, you can say. And this is fully filled or completely filled. So fully filled have more ionization enthalpy than the half filled one. Or you can even give this reason, that nuclear charge increases, size decreases. Size and ionization enthalpy are inversely proportional, so ionization energy will increase. Now this was for your first period. Let us talk about period number 2. Let us talk about period number 2. We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Yes, everybody. First of all, write down, the general trend. When general trend is, when you are moving from left to right, nuclear charge increases. Very simple. If nuclear charge is increasing, ma'am, that means the size is going to decrease. If size is going to decrease, ionization enthalpy will increase, because they are inversely proportional. Also, ionization enthalpy is directly proportional to nuclear charge. So it will increase. This should be our trend. But yes, there are some exceptions. What are the exceptions? The second factor was electronic configuration. Let us write the atomic number of all of them. 3, 4, 5, 6, 7, 8, 9 and 10. Let us write the electronic configurations now. Electronic configuration will be 1s2, 2s1. For this it will be 1s2, 2s2. For this it will be 1s2, 2s2, 2p1. For this it will be 1s2, 2s2, 2p2. For this it will be 1s2, 2s2, 2p3. For this it will be 1s2, 2s2, 2p4. For this it will be 1s2, 2s2, 2p5. For this it will be 1s2, 2s2, 2p6. Yes? Now see, students. See, 1s2 is completely filled in all of these. In 2s1 it has 1 electron. In 2s2 it is completely filled. Let me take another color. In 2s2 it is completely filled, but in P it has 1 electron. Over here in P it has how many electrons? 2 electrons. Over here in P it has how many electrons? 3. 1, 2 and 3. Over here in P it has 4 electrons. So 1, 2, 3 and 4. Over here in P it has 5 electrons. So P basically has 3 orbitals, no? So 1, 2, 3, 4 and 5. Over here it has 6 electrons. 1, 2, 3, 4, 5 and 6. Which of them is completely filled, students? Which of them are completely filled and partially filled? Just write it with yellow one. See, this is fully filled. Okay. This is half filled, having 1 electron in each, and this is fully filled. So what will happen? Basically this is half filled, so its value will be more than its first atom. If oxygen is present initially, so it will have more value than oxygen. Here beryllium is fully filled, so it will have more value than boron. Here it has the highest value. It has the highest value. So what will be the order? Order will be neon will have highest, then fluorine. Now oxygen won't come. Here nitrogen will come. Why nitrogen? Because it is half filled, so it is quite stable. Its value will be more than oxygen. then it will be oxygen, and then it will be carbon. After carbon, it won't be boron, it will be beryllium. Why? Because it is fully filled. Then it will be boron, and at last it is lithium. So this is the correct trend. This is the correct order, students, for your ionization enthalpy. This is your correct order for ionization enthalpy. Everybody write it down properly so that I can move on to the next part. Everybody write it down properly so that I can move on to the next part. Done? Shall we move on to the next one, students? Okay. Now, students, there is one homework question. Question 1 as a homework is, write the order for ionization energy for period number 3rd. I have written for period number 2nd. You have to write for period number 3rd. This is your first homework question of today's class. First homework question. Let me take it down. This is your first homework question for today's class. Clear? Sorry. Coming back to our topic now. Now comes the variation along the group. See, in group it is very simple. If I am talking about group number 1 and 2, it's very simple. Hydrogen, then I have lithium, sodium, potassium, rubidium, cesium and francium. What is going to happen in group 1 and 2, that is alkali metals from top to bottoms, alkali metal, alkaline earth metal, size basically ma'am increases. Why? Because number of shells ma'am increases. If size is increasing, ionization enthalpy will decrease. This is so for the group 1 and group 2. But for P block elements, let me show you that for boron family, again group number 13th, see how it occurs. You have to learn this with the help of a trick, that is with the help of W. You have to draw W like this. Okay, now place the elements of the boron family. What are the elements of boron family? Boron, aluminium, gallium, indium and thallium. Place it like this. Boron, aluminium, gallium, indium and thallium. Now see which has the highest value, boron. After boron, which has the value? After boron it's thallium. After thallium it's gallium. After gallium it's aluminium. And after aluminium it's indium. So see like this, no? See in a mathematical form. Which has the highest? This, then this, then this, then this and then this. So this is going to be the order. By this way you have to learn the exception for the P block family. Clear everyone? Everyone, is it clear to each and every one of you? So write it down so that I can move on to the next part of yours if it is done, students. Shall we move on to the next part? So this ends our ionization energy. Let us read from the NCERT highlight. What does NCERT says? Now I have already told you that we are going to discuss topic from the NCERT also, because in organic chemistry, NCERT purpose is really important and we are basically discussing topic to topic wise. So let us see about what does this say about ionization energy. It represents the energy, you can even write down, we are talking about ionization energy. So see, it represents the energy required to remove an electron from an isolated gaseous atom in its ground state. When you are removing one electron, the energy required is ionization enthalpy. Energy is always required to remove electron from an atom, and hence ionization energy is always positive. Is always what? Is always positive. So this is very, very important thing that you should know. Next is, the second ionization energy will be higher than the first one. Already told you. The third will be more higher, yeah? Because force of attraction becomes stronger. So, because it is more difficult to remove an electron from a positively charged species than a simple neutral one. Similarly, the third ionization energy will be higher than the second one. The term ionization enthalpy is not qualified. It is taken as the first ionization enthalpy. So, you always say first ionization enthalpy. That means first electron is being removed. Second means second being removed. Third means third being removed. So, this is the way how it works, right? Now, there is one more question as a homework. This is your question number 2 as a homework, which is your NCERT in-text question. Problem 3.6. The first ionization enthalpy values of the third period elements elements, sodium, magnesium and silicon are respectively provided to you. Predict whether the first ionization energy for aluminium will be more close to this or this. Justify your answer. They have given you the values. Yeah, so this is one more homework question, NCERT in-text question 3.6. You can pause the video and write it down, students. Next question as a homework which I have already given to you. Yeah. Now starting with the next topic, that is electronegativity. I will give you a brief intro about electronegativity, then we will end up the session because next we will be left with the next properties and we will be cover the next part with that. What is electronegativity? Already explained you when I was explaining you about covalent radii. Yeah? So electronegativity basically is the tendency to attract shared pair of electron towards itself. If I am electronegative in nature, I have a tendency to attract electron towards me. I am just attracting. I am not breaking a bond. I am just attracting. So this is what is attraction of the tendency to attract a shared pair of electron is electronegativity. The electronegativity is a measure of tendency of an element to attract shared electron towards itself in a covalently bonded molecule is electronegativity, also represented as En. Okay. The magnitude of electronegativity depends upon ionization potential and electron affinity. Ionization potential, enthalpy you have already studied. Now only we have done electron affinity in the next class. Higher the ionization potential and electron affinity value indicate higher electronegativity value. See, all the trends, you know, basically they all are inversely proportional to size. If size increases, ionization enthalpy will decrease, electron affinity will decrease, electronegativity will decrease. So the factors are quite same for all of them, yeah. Next. Now see, the electronegativity things they are explaining you. So I am telling you the factors. The very first factor is electronegativity is inversely proportional to size. Yeah. Electronegativity will become higher if the size is small. Why? Because it is attracting. It has a tendency to attract. If size is small, it is attracting the shared pair of electrons. So electronegativity is something which is high. So it is inversely proportional to size and directly proportional to nuclear charge. Quite simple? Quite simple? Yes. Electronegativity is directly proportional to positive charge and inversely to the negative one. See, when atomic size increases, the distance between nucleus and the valence electron increases, right? Atomic size increasing, the distance increases. Thus, force of attraction between nucleus decreases, electronegativity also decreases. So that means electronegativity is inversely proportional to size. If size you are increasing, force of attraction decreases, electronegativity will decrease. If size is basically decreasing, it is coming close, so electronegativity will increase. Got my point, everyone? So now next homework question for your today's class is third homework question. I am writing it over here only. Question third as a homework is write the order for group 1 and 2 for electronegativity by your own. Rest I will do. It's quite simple. I'm saying there is no exception. Quite simple. Electronegativity, no exception. Quite simple. And one more question. Which is the most electronegative element? Most electronegative element among the whole periodic table. This you will be able to tell me by writing the trends in periods and group, and it's very easy, no exception, again repeating. I guess homework you have written. So students, the rest of a part of electronegativity we will be covering in the next class with our electron affinity topic. And yes, I have already told you in the previous session that we will be doing questions of the previous session. But yes, I thought that periodic properties question we can discuss all together, because the trends, I have given you the exception of trends of atomic radii of period third in this session only. So I have told you that we will be doing it all together. But yes, in the next session we will be covering electron affinity, electron gain enthalpy, periodic properties will finish up in the next segment. That means in the next session. And we will be practicing the previous year questions of the periodic properties in the next class. So everybody be prepared for that. Do revise each and every topic of this chapter. Yes. Now I shall meet you in the next lecture. Till then, keep smiling, keep learning. Thank you so much and take care, everybody.